Hi kids, so this video is for class 10 student. We were solving circles from L Aggarwal and we already did exercise 15.1 and 15.2. 15.1 was based on angle properties of circle and 15.2 was based on cyclic properties of circle. In this video, we'll look at the tangent and secant properties of circle and then we'll solve sums from exercise 15.3. But before solving the sum, you should be aware with all the theorems and the properties. Okay, just look over here first. Suppose in this plane, I draw a circle and a straight line. So three cases can arise. First of all, look carefully. There's no contact between the circle and the straight line. Second case can occur that the straight line passes through the circle like this. It intersects the circle at two different points. When a straight line passes through a circle, it will always intersect at two different points. Then there is one more case. Look carefully. It can happen that the straight line just touches the circle. Mind it, touches the circle. Touches the circle at one point, suppose P. Then this line is known as the tangent of this circle, and this line, where the line intersects the circle at two different points, is known as the secant. This is your tangent and this is your secant. Understood? Now look over here. The first very important theorem which we should remember in case of a tangent, that, okay, over here I'll do. Suppose this is the center of the circle and you draw a radius from the point P. So this OP is the radius. So the first theorem which we should know is that suppose this line is L, that OP, the radius, is perpendicular to the line L. The tangent at a point of a circle is perpendicular to the radius from the same point. These two are perpendicular. The radius is always perpendicular to the tangent at the point of contact. Okay, now look carefully. How can you prove this? Look carefully. Suppose I take a point Q on this straight line anywhere. I'll join OQ. And suppose this is R. Now look carefully. OR and OP is equal? Yes or no? Which means OQ is greater than OP? Definitely. Because OQ is OR plus RQ. Just look carefully. OR plus RQ, of course, is greater than OP because OP and OR are equal. OP is equal to OR. So this will happen. Which means, try to understand this. You take any point over here, any point. OP will be the shortest distance. OP is the shortest distance from point O to the line L. Try to understand this. OP will always be a shorter distance. You take any point. You take, suppose, over here A, over here B. Again, OP is less than OB. OP is less than OA, which is OP will be smaller than all other line segment. Yes or no? And we already know that the shortest distance from a point on a line, if I say you that OP is the shortest distance, OP is the shortest distance, if I tell you the shortest distance from a point on a line is always perpendicular, which means we can apply over here. OP is the shortest distance, we know, which means OP will be perpendicular to L. This is our first theorem. The tangent of a circle at a point P is perpendicular to the radius from the point P. Okay, this was your first theorem which we should know. Let us look at the converse of this. Look at the converse. A line drawn through the end of the radius and perpendicular to it is a tangent to the circle. See, what is the theorem we have done? That this is a circle, this is a tangent, this will be perpendicular to the radius is perpendicular to the line. OP is perpendicular to L. OP is perpendicular to the tangent. L is tangent, we know. Hai ki nahi? This was a theorem which we have done just now. The converse. A line drawn through the end of the radius. So, this is your circle. This is the end of the radius. And if you draw a line through the end of the radius and perpendicular to it. So, I need to draw a line which is perpendicular to it. OP is perpendicular to L. Okay, over here we knew that L is tangent. Okay, over here we need to prove that this is a tangent, which means this line L touches the circle at only one point. That we need to prove over here. देखो कैसे करते हैं. A line drawn through the end of the radius and perpendicular to it is a tangent. We need to prove that L is a tangent. Look, again, take any point Q. Join कर दो. OQ is greater than OP. OQ is greater than OP. And OP is the radius. OP is the radius. So the point Q, since OQ is greater than OP, so point Q lies outside the circle. Yes or no? And OP is the shortest distance. This is shortest distance. Yes or no? From O on this line L. OP is the shortest distance because it is perpendicular, so it is the shortest distance. OP is perpendicular to L, which means it is the shortest distance. Now, you take any point, on this line, it will always be this, suppose OA, OB. This OA is always greater than OP. OB is always greater than OP. Yes or no? Which means this A, B, Q, any point, Z, Y, X, they all lie outside the circle because the length is greater than the radius. So these all point lies outside the circle, which means there's only one point P that lies on the circle and the straight line passes through the point P. Yes or no? Which means L is what? The tangent, because there's only one point of contact. Only one point of contact, isn't it? So we can say that L is the tangent because we just saw, you take any point on the line L, it lies outside the circle except the point P which lies on the circle. Hence we can say that this line L is a tangent because it touches the circle at only one point. So here this was the theorem that the radius and the tangent at the point of contact, they are perpendicular to each other, and this is the converse of this theorem. Done. Sure. See some outcomes based on these properties. Okay. Now based on whatever we have done till now, we have these three conclusions you can see. First one and only one tangent can be drawn to a circle at a given point P on the circle with center O because only one perpendicular can be drawn to OP through P. What does it mean? That if you have a circle if you have a point P on the circle, then you can draw only one tangent. From the point P, you can't draw more than one tangent because there will be only one perpendicular line which you can draw from the center on that line L at point P. Yes or no? If you draw another line, that won't be a perpendicular. Hence, you can say that only one and only one tangent can be drawn from this point P, not more than one. Next, let me see what they have given. The perpendicular from the center of a circle to a tangent passes to the point of contact, which means if you just extend this term, so the perpendicular from the center of a circle to a tangent, this OM is perpendicular to the tangent, it passes to the point of contact. This is the point of contact. So this perpendicular, if OM is perpendicular, then it passes through P. This OM will not pass through some other, point. The perpendicular will always pass through the point of contact. Number 3, if the perpendicular to the tangent through its point of contact, passes to the center, which means if I draw a circle, if there is a tangent, and at this point P, if I draw a perpendicular, then it will pass through the center, because the perpendicular, which means it will be the radius. From the center it will be the radius, and the radius always passes through the center, you can say. Yes or no? That one is these are all the outcomes, Now, one thing, how many tangent you can draw, let us see. I'll take 3 cases. How many tangent you can draw to a circle? First, number of tangent, okay? Number of tangent, we'll see. I'll take a point inside the circle. Then can we draw any tangent from the point P on the circle? No, never, because any line which passes through this point P will be a secant, it won't be a tangent. So you can't draw a tangent from a point inside the circle. Okay? Now, number 2. Suppose the point P lies on the circle, then you can draw only one tangent. Abhi to kiya. Only one tangent you can draw. Only one tangent. And now, very important. These two are clear? Dhyan se. If the point P, in the first case, it was inside the circle, no tangent. On the circle, one tangent. If the point P lies outside the circle, then from the point P, how many tangents you can draw? 2. Look over here. This is PA, PP. From a point outside the circle, we can draw maximum 2 tangents, not more than 2 tangents. And this PA, this segment of this line, this is suppose L1, this is suppose L2 line. Okay, then this PA and PB are known as the length of the tangent. Length of the tangents. Am I clear? So from a point P outside the circle, you can draw 2 tangents, and PA and PB are known as the length of the tangents. And now based on this, our next theorem, which is very important. Now just now we did that 2 tangents can be drawn from a point which lies outside the circle. So these are my theorems from that particular point. What? If 2 tangents are drawn from an external point of a circle, so what I'm doing, This is my circle. This is a point, tangent, okay, and this is my another tangent. Suppose this is PA, this is PB, and this is the center O. Look over here. The length of the tangent are equal. First thing, the length of the tangent, PA, I told you PA and PB are equal. We'll prove it. The tangent subtend equal angle at the center, which means join this, and if we join this, then the tangent subtend equal angle at the center, which means this angle and this angle is same. Angle AOP and angle BOP is same. We'll prove it. And third one, the tangents are equally inclined to the line. The tangents are equally inclined to the line joining the point and the center of the circle, which means this and this angle, both are same, which means we need to prove that angle OPA is equal to angle OPB. We need to prove this. Look carefully, very easy. In triangle AOP and triangle BOP, AO is equal to BO. They both are the radius. Yes or no? Then PO equals to PO. That's common if you look at the diagram. And this is perpendicular. We know the radius and the tangent, they're perpendicular. So I can say OAP, angle OAP is equal to OBP. That is equal to 90 degree. Which means these two triangle AOP is congruent to triangle BOP by RHS, right angle, hypotenuse, and one of the side is equal, RHS. Now, if they are congruent, then the corresponding part of congruent triangle are equal, which means PA will be equal to PB, CPCT, angle AOP is equal to BOP, CPCT. Yes or no? Angle OPA is equal to angle BP, OPA and OPB, CPCT. Yes or no? This is what we were supposed to prove. That's the theorem only. PA equals to PB. This angle and this angle are equal, and this angle and this angle are equal. That's the theorem. Done? Now let us see touching circles. Okay? Now look at touching circles. Now, touching circles. Now, two circles can touch each other in two ways. First is, this is your circle 1 and this is your circle 2. They touch each other externally. Suppose the center of this is A, this circle, the center is B, this is the point P, which is the point of contact. Okay, they touch each other at P. Then remember one thing, this A, P and B lies on the same straight line. I'll prove this. And you will have one common tangent. This is the common tangent. Okay. Now somebody can say that these two circles touch externally. Now we can have a scenario where the two circles touch each other internally. This is also possible. This is the point P. This is the center of the smaller circle and this is the center of the bigger circle. Then again, this lies on the point A, B and P are collinear. They lie on the same straight line. Okay, and again you will have one common tangent. So if two circles touch externally or internally, you will have one common tangent. And the centers of the two circles and the point of contact of the two circles they lie on the same straight line. How? Just look over here. AP is the radius for this bigger circle, and since this is a tangent, L1 is a tangent, so this angle is 90 degree, no doubt. We have already done. Similarly, BP is the radius for the smaller one, and L1 is a tangent, so this angle is 90 degree. Now, these two angles, see this is C, suppose, APC, angle APC plus angle BPC, 90 plus 90 is 180, so these two are linear pair. Yes or no? These two add together to give 180, which means ABP is a straight line. Yes or no? Sure. Now, and this we know. See, this makes AP, this is 90 degree. This makes also 90 degree. So AP on this line L2, suppose, the angle APC is 90 degree, BPC is also 90 degree. So they have to lie on the same straight line. Yes or no? Now, suppose the two circles do not meet at a point. In this case, we say that they touch each other externally or internally. But what happens? How many tangents we can draw if they don't touch each other? If they touch each other, we have one common tangent. And the most important thing, the point of contact and the centers of the two circles lie on the same straight line. That was very important. Now look at this scenario when the two circles do not touch each other. Okay? Then look over here. We can have, I can draw a common tangent like this. Look carefully. I'll just increase it. Okay? I can draw a common tangent like this. I can draw one more common tangent like this. So I can have two common tangents, and both the common tangents are on the same side of the circle. Okay? So these two are known as direct common tangent. They lie on the same side of the two circles. See, this tangent L1 and L2. L1 lies on the top, L2 lies on the bottom. Now, it may happen, these two are known as direct common tangent. There are two common tangents over here, okay? Now, it may happen, we can draw a tangent like this also. See carefully. L3 and one more. This L4. Now, if you look carefully, this L3 and L4, this is the line. The circle lies on either side, on the opposite side. One on this side, one on that side. So these two are also common tangent. They are known as transverse common tangent. Okay? And these two are known as direct common tangent. They lie on the same side. The circle lie on the opposite side of the tangent, if you look carefully. Okay? Now, this is clear, I hope. Two direct common tangent, two transverse common tangent. Now, segments of the chord. This is very important. Now consider a chord, two chords, be careful, inside a circle which are not parallel. Then they can intersect inside the circle internally. A, B, C, D, a chord. They meet at a point P. We can have a situation where the two chords meets outside A, B, C, D. Outside the circle, they can meet internally, they can meet externally. So P divides AB in the ratio, just look carefully, AP is to PB internally, and P divides CD in the ratio CP is to PD internally. This was internally. That's externally. So we can write again P divides AB in the ratio PA is to PB, and P divides CD in the ratio PC is to PD. Again, externally. This was externally. It divides externally. This was internally. So, in this scenario, in this kind of scenario, when the two chords are not parallel to each other, so they'll either meet internal or external. Then the product of the segments of the line will be equal, formed by the two chords. What I mean by that? See, P divides AB in the ratio AP is to PB. So there are two segment forms, AP and PB. In this case also, P divides CD in two parts. So the segment forms are CP and PD. In this also, PA and PB, one segment, and the other is PC and PD. So my theorem states that if two chords intersect internally or externally, then the length of the segments, the product of the length of the segments are equal, which means if you multiply AP and PB, this will be equal to CP into PD. If you multiply PA into PB, this will be equal to PC into PD. How come? PA into PB equals to CP into CD, PA into PB is equal to PC into PD. How come? Just look over here. I'll join this. Okay? These two triangles, you see, I'll prove them similar. This angle and this angle is equal, vertically opposite angle, and this angle is equal, angle in the same segment, see, angle CAB is equal to angle CDB, angle APC is equal to BAPC, D rather, I should write properly, DPB. Same segment, look carefully, this is the same segment and this is vertically opposite angle, which means these two triangles are similar. Now if they are similar, we have done it in similarity. So the corresponding sides are proportional to each other. See, I just proved that triangle APC is similar to triangle DPB. So I can say AP by DP is equal to PC by PB is equal to AC by DB. We have done in similarity. The corresponding sides are proportional to each other, which means now look at these two, cross multiply. AP into PB is equal to DP into PC. DP into PC. Done. Over here also, we'll do the same thing. Look over here. What I'll do, I'll join this and this. This angle is common. And we know ABCD, ABDC over here. ABDC is a cyclic quadrilateral. So this angle and this angle will be equal. Exterior angle equals to opposite interior angle, which means the triangle, look carefully, APC is similar to, A corresponds to D, triangle DPB. If they are similar, AP by, actually we wrote here wrong, this will be D, by DP is equal to AC by DB is equal to PC by PB. Yes or no? Equate these two. So AP into PB is equal to PC into TP. Done. This is a very important theorem. If two chords intersect, then the product of the line segments are same. Now, there are two more theorems which we need to know. Okay, let us see the next one. But this is a very important theorem. Angle in the alternate segment. If a line touches a circle and from the point of contact a chord is drawn, The angles between the tangent and the chord are respectively equal to the angles in the corresponding alternate segment. Look, we'll draw and then you will understand. Suppose we have a circle like this. There is a point P and we draw a tangent. From the point P, we draw a chord. Okay? Then the angle between the chord and the tangent. See, if a line touches a circle and from the point of contact a chord is drawn, then the angle between the tangent and the chord, this angle, first of all I'm taking, this angle is also there, I'm taking first this angle. The angle between the tangent and if this is my angle, between the chord are respectively equal. This is equal to the angle in the corresponding alternate segment, which means if I form at this segment, I form this angle. Then this angle and this angle is equal. Similarly, in this segment, if I form suppose this angle, then this angle and this angle is same. Just remove the red one, okay? I'm taking one segment only in one alternate segment because the other one has the same proof, okay? Look carefully. If a line touches a circle and from the point of contact a chord is drawn, the angles, there will be two angles, this one and this one. The angle between the tangent and the chord are respectively equal to the angle in the corresponding alternate segment. For this angle, this is the alternate segment. For this angle, this is your alternate segment. If you take this angle, then you form a segment like this, which I formed. If you consider, try to understand this angle, then this is my segment. These and this will be equal. Okay, I'll do the proving for one. Okay, so I'm just removing this. Now look over here. Suppose the center is O. Then I'll join PO. I'll join PO. So this is O. This is suppose A. Then PA is the diameter. This is C. I'll join this. Just look over here carefully. Try to understand this, okay? This is my P. Try to understand. Focus over here. Now, very interesting. We need to prove that this angle and this angle are equal. This is suppose D. First of all, this is 90 degree. Angle at a semicircle. Angle ACP equals to 90 degree. Angle at a semicircle. Done. Now, this angle is 90 degree. Radius and tangent. So APE, angle APE is 90 degree. Any doubt? Now if this is 90, then this plus this will be also 90 because the angle, some property, sum of angles will be equal only, will be equal to 180. So in triangle, look carefully, ACP, angle ACP plus angle CAP plus angle APC is equal to 180. Angle some property, ACP is 90. So 90 plus angle CAP plus angle APC is equal to 180, which means angle CAP plus angle APC equals to 90. So this angle and this angle is 90 and these two angles are 90, which means I've already done APC, angle APC plus angle CPE is equal to 90 because this entire angle is 90. So these two also add to get 90. Equate this and this. Angle CAP plus angle APC is equal to angle APC plus angle CP. Try to understand. APC cancel, which means CAP. This angle, look carefully, and CP, this angle are equal. Yes or no? So if this is X, this is X. Done. Now look carefully. Angle CAP is equal to CDP. This angle and this angle. This and this both are equal. Same segment. From CP we have drawn. Same segment. Yes or no? Angle in the same segment are equal, which means indirectly we can say that directly matlab this angle and this angle are equal, which simply implies angle CPE is equal to angle CDP. Proved. This angle is equal to this angle. Now look, if a line touches a circle at a point P and from the point of contact a chord is drawn, the angle between the tangent and the chord are respectively equal to the angle in the corresponding alternate segment. Similarly, if we have something like this, then this angle and this angle will be equal. Remember this. Done? This was very easy. Now we have one more theorem. We'll look at this, okay? A very interesting theorem. If a chord and a tangent intersect externally, so suppose this is your chord and this is your tangent and they intersect externally. This is A, P, this point is C, suppose. Point of contact of the tangent with the circle, and AB is a chord, and they meet each other externally at P. Then the product of the length of the segment of the chord, product of the length of the segment, which means PA of the chord, PA into PB, PA into PB is equal to the square of the length of the tangent. Length of the tangent is PC, square of the length of the tangent from the point of contact to the point of intersection. This is the theorem. How to prove this? Very easy. Just join this and join this. First thing, this angle just now we did and this angle are equal. Angle in alternate segment. Look at triangle B A P C. Talking about A P C. And look at triangle CPB. First of all, angle PAC is equal to angle PCB, angle in alternate segment. Then angle APC is equal to angle CPB, that's common angle. Look over here, which means these two triangles are similar. Triangle APC is similar to triangle A corresponds to C, CPB. Now, if they are similar, we know the corresponding sides are proportional, which means AP by PC is equal to, we can write AP by CP is equal to PC by PB is equal to AC by BC. Yes or no? Take these two. So AP multiplied by PB equals to PC into PC is PC square. That's the theorem. Done. For the chord PA and PB will be equal to PC square by similarity. Very easy. Angle in alternate segment, this is the common angle. Done. They are similar. Then if two triangles are similar, the corresponding sides are proportional to each other. वो use किया. Done. So these were the theorems which are necessary before we move to the next exercise of circle, which is exercise, I think part 3, 15.3. So in this video, we'll keep it till here. In the next video, we'll look at the numericals, look at the sums from exercise 15.3. This is a very important lecture, If you have understood this, then the entire exercise becomes easy. Okay? Sure. If you like this video, do subscribe and share with your friends. Everybody take care and have a nice day.